teaching strategies to overcome poor standards of interpretation. Some statisticians have been concerned for years over standards of interpretation in published research. But is there anything we can do about it? And does it really matter? Well, I'm justifying why I feel it does matter, and I'm also offering some practical teaching strategies that are relatively straightforward that I feel would steer people away from these misconceptions. My view is also that some of the ways we teach statistics is leading people towards these misconceptions in the first place. I certainly feel research politics is also an issue here. I'm not really going to talk about that further because it's a challenging issue and it's quite a separate issue. So at least I do feel I can make a contribution here by offering some methods of stats teaching which are designed to improve standards in the published literature. Okay, yes, a rather lofty aim, but at least I feel it's a step in the right direction and a practical step. My starting point was an obsessive interest in teaching stats and my sense that there's ways in which we could make it easier for people to understand. And indeed, there are times when I've been told that I've got a reputation for making stats easy to understand. So I have used these methods successfully. The agenda: concerns over standards of stats interpretation in the literature and why it matters. Evidence of poor understanding amongst some people of p-values and confidence intervals. And then my considerations: why are they hard to understand with current teaching methods? And I've got a number of issues and suggested teaching remedies. There's concern about people ignoring calculated odds ratios. I'm mostly talking about odds ratios. That could apply to relative risk, incident rate ratios, whatever. Ignoring confidence intervals, perhaps because they're misunderstood. Images that teach confidence intervals can be misinterpretations. There's direct evidence from surveys that p-values interfere with the interpretation of calculated odds ratios, and some people think that genuinely isn't an association, perhaps, when p is greater than 0.05. And there's concern over excessive focus on p is less than 0.05 rather than interpreting p-values on a continuous scale. And so I'm presenting the issues and teaching remedies and then some conclusions. Now, this was originally a live talk for the RSS Statistics Education section. There were technical issues, so it wasn't able to be recorded at the time. I'm not actually going to be talking about the discussion in this recording, but I'm planning a brief separate recording that talks about it. There was also a science comedy video at the end, an online one of my live act. Key concerns from the literature. This is from a Nature publication, 2019. Around half of all publications report no association, erroneously based on p greater than 0.05 alone. This is true in medical research, which is my own area, and it's also true in various other areas where there were surveys done. Some studies go further by claiming to have proven no association, erroneously based on p greater than 0.05 alone, even when the odds ratios that they found were of clinical importance or practical relevance. And some people describe two studies as incompatible because only one of them found p less than 0.05, even when they both found virtually the same odds ratio amongst their participants. Now, systematic reviews, I guess ideally these days they have meta-analyses, but they don't always. And some people compile the evidence with a primary focus on whether individual study results show p is less than 0.05. Certainly the Cochrane collaboration is concerned with that and directly refers to that as a problematic way of doing it. Even if you want to keep things really, really simple and you've got a number of different measures of anxiety or whatever it is, so it's hard to numerically summarise the evidence, there's still strategies that are better. Simply counting how many have got estimates in the same direction of association, and how many have got associations in a different direction. That is much better than counting which have got p is less than 0.05 and virtually is straightforward. And that the latter one is supported by Cochrane as a reasonable way of doing it. And I'm going to justify why the lack of ability to sensibly summarise evidence across studies. This has implications for treatment and lifestyle advice. And so if you're obsessing too much on whether p is greater than 0.05 in individual studies, you can't appropriately say which are compatible, and you can't necessarily summarise evidence in a sensible way. Here's an example: odds ratio of bowel cancer. This is made up data, to be honest. Odds ratio when consuming food agent X compared to not, with confidence intervals. So we've got 4 studies here. Each of them, the odds ratio is about 1.4, 1.5, and confidence intervals. But all the confidence intervals overlap 1, so we're going to have p greater than 0.05 in each case. So if we interpret this as no association simply because p is greater than 0.05, we've got 4 studies finding no association, and so you might then conclude that this is pretty strong evidence overall that we've got no association. But if you did a meta-analysis, then you'd find a completely different answer. We've got pretty good evidence that the odds ratio is, it could be somewhere around 1.4, 1.5, a lot of consistencies between the studies in that, and we would have p less than 0.05 for the result from a meta-analysis, a confidence interval that wouldn't overlap 1, because each of the individual confidence intervals, they don't overlap 1 that greatly. So we'd have quite a different conclusion. So this does demonstrate how dangerous it is to refer to individual results with p greater than 0.05 as no association when you're wanting to make sensible summaries across the literature. And of course, practical advice is usually based on summaries of evidence across the literature, so this really matters. Maybe this is because people don't understand. I'm sure nearly everybody realises that a lot of students find stats courses challenging, and there's evidence that it's got a reputation for being a particularly challenging subject, with a lot of people being required to take a stats course in all sorts of different degrees, even though they might really not like having to do that. There's direct evidence that p-values and confidence intervals, that some people have misunderstandings of them. Some educators share these, and this includes amongst people that did well in exams. I've also got anecdotal evidence. Some people that have ended up as professor of statistics have acknowledged that they only gradually gained an understanding of these things in the first few years of their careers. There's a reader in medical statistics education who openly speaks at conferences that he didn't really understand p-values until he had to teach them. And he's open about that because he's concerned about this being an issue. Now, my view is that because we don't really focus much on conceptual understanding, what are they about, what is their purpose, there can be a lot of focus on how to calculate them and what are they all about. The conceptual understanding can be somewhat overlooked in courses, which is why I've proactively focused there. Why are they hard to understand? The definitions don't give much sense of the practical purpose of p-values and confidence intervals. The definition of a confidence interval feels to me like a property of a confidence interval that everyone should know, and not a definition because it doesn't hint at what a confidence interval is for. In formal interpretations of confidence intervals, we could say we're 95% confident population mean is within this interval, which is okay, it's simple. It's obviously only crudely correct or wrong according to your stance. But if you agree it's loosely correct, the issue is that it relies on people understanding the word population, and that's not necessarily easy to understand. So if we're going to repeat a confidence interval interpretation because we want people to understand, then we could consider also repeating some sentence that indicates who the population is and what their relationship is with the participants that we've recruited. Clearly, when I'm talking about participants recruited, I feel that makes it a bit clearer than observations, and it's mostly relevant within medical research when they're usually participants. But I do appreciate in different settings, it might be that we're talking about different types of objects as our observations. I've also got a bit of an issue with the fact that the definitions are based on taking very many random samples, and many random samples exist within computers of statisticians in their simulations. It doesn't represent a practical study design. And so that can make it a little bit difficult to think, well, what is the practical relevance of this? Because it's talking about these simulations. Informal interpretations, maybe particularly if p-values are too crude to be of much help. If you say p less than 0.05 statistically significant, that makes it sound as if it's large enough to matter clinically, to practical relevance. And so the very terminology you're using is potentially distorting the meaning of p-values. And so if you think the definition is a bit cumbersome and move towards an interpretation using the word significance, then in my view you're distorting what a p-value is, because it's all too easy to feel that means it's big enough to matter. Focus on calculation methods. The distribution of sample statistics are notoriously hard to understand. So below there's the t distribution with errors representing the p-values, and that's the distribution of, it could be the difference in means on some standardized scale, and this is if you get very many random simulations of the difference in means based on random sampling from some theoretical populations of known size, and then you standardize. This is the distribution you get for these many random simulations, and this is the distribution under the assumption the null hypothesis is true. It's not that straightforward a thing for people to understand, and so I mean it's absolutely fine so far as I'm concerned to show these distributions, but I think that we may rely on them too much, and we could at least add in some other illustrations that help us understand the concept of what confidence intervals are. So there is a concern over ignoring calculated odds ratios and just saying p is 0.05, no association, when the odds ratio might be quite large. If it's all-cause mortality, in comparing smokers with non-smokers, an odds ratio of 1.18, 8% increase in all-cause mortality is clinically important. And so we shouldn't really be just dismissing this as no association, even though we might say no evidence for an association. Now, in my view, I question why in statistics lessons we tend to talk about odds ratio in the sample, or the point estimate of the population odds ratio, the best estimate. I mean, maybe it's okay, but estimate or sample, these slightly downplay their importance because it's emphasising that random chance means it might not be correct, which is true, and yet it still is the best estimate we've got. So I prefer to talk about the odds ratio amongst study participants, or the calculated odds ratio. And I feel this language gives a bit more emphasis to their importance. It's also really clear. When one observation is a study participant, it's absolutely clear who we're talking about if we say odds ratio amongst participants. But if we say in the sample of the population, well, the population is quite a challenging concept, because certainly in medical research we haven't usually selected people actually at random from any population. So it's the population that we theoretically imagine that we would have selected them at random from. So why are we talking about referring effectively to the study participants as a sample of the population, which is a much more convoluted way of thinking about who they are? In my view, if you have this really clear starting point, confidence intervals become easier to understand because it contrasts the fixed known value amongst study participants, and then it's clearer to people where the uncertainty comes from in the confidence intervals. And I also tell them where it comes from. Okay, so this may be some small step towards encouraging people to interpret odds ratios. Why might people ignore confidence intervals? As I say, it could be because they don't understand them. I'm not personally a great fan of the definition of confidence intervals. I consider it a property of confidence intervals that everybody should know, rather than something that's very useful for actually telling people what is a confidence interval and what's its purpose. Informal interpretations might be too much dependent on people understanding the word population, but it is possible to augment informal interpretations with sentences that say who is the population. This is one way you might interpret the confidence interval. So odds ratio is, so starting with a clear statement, it's 1.18 among study participants. The study data is readily compatible with random selection from a population that has odds ratios between 1.02 and 1.36. So we're talking about compatibility, we're referring to the assumption of random sampling, and we're effectively defining a population because it's the group which our participants were theoretically selected at random from. And so that gives much more of a sense of what a confidence interval is. And so maybe this sentence alone is worth repeating throughout teaching material to give much more of a sense of what a confidence interval is. There's various different alternatives. One drawback is this doesn't talk about 95% level, so we could add a sentence gives 95% coverage of compatible levels, or simply say readily compatible at 95% confidence interval. We can add other sentences, reflect precision of estimated population odds ratios, and this is when generalising beyond study participants, accounting solely for assumed random choices in their selection. And generalising beyond study participants is arguably a key purpose of what confidence intervals are about, because we're wanting to make inferences about this population, assuming random selection from them. I'm actually currently doing another paper on confidence intervals where we had a survey of medical statistics educators that gave all sorts of different versions. I mean, there was one version, this is pretty much what I recommend to interpret confidence intervals in this paper. I don't feel you should think of it as set in stone. Maybe the full definition's a little bit long, and it might maybe it's better to have a version that's not too long to develop conceptual understanding. But I think the whole idea of moving away from the standard definitions and really considering the language that we use to say what is a confidence interval. And many people throughout teaching material will keep on asking students to interpret confidence intervals. And so it's really worthwhile there to make really clear, explicit choices over what language you use when you're interpreting it and what language you expect your students to use. So what language do you think will best reinforce the definition of confidence intervals? It's not necessarily the precise language I used here, because that's not quite what we use in teaching practice. It might be a bit long, but just the idea that you can move away from standardly used forms of wording and get something potentially that serves the purpose better of developing students' understanding. That's the key idea I'm wanting to get across here. Now, I've also got a concern that confidence intervals can be this diagram. This does usefully indicate how confidence intervals are calculated. So, for instance, if it's a confidence interval on a mean, then we're looking at the t-distribution, or for a difference in means, it's also the t-distribution. And this shows the tail areas and how we find the cut-offs to calculate our confidence intervals. But the issue I have with this is that these are notoriously difficult to understand, these distributions, exactly what they represent. And if you look at this quickly, you might imagine the interval within the confidence interval, it's demonstrating 95% coverage. So if you don't really know what it is, you can very likely interpret it as 95% coverage of the observations themselves. So you might think 95% of all cholesterol levels will lie within the confidence intervals. And in many years of teaching and all sorts of different situations, some students always have that misconception. I mean, I do deliberately ask questions to see if they're going to fall in that trap, because I feel it's important to root that out and correct it. But that's such a major misconception that confidence intervals are about spread or variability in the data. It's just completely wrong. And so it really matters to me to correct that. So my recommendation is, if you want to include an image like this that illustrates how you calculate confidence intervals, then also include some other images that offset that visual impression. And I feel this exercise is really useful for giving people a sense of what a confidence interval is. It works when you've got confidence intervals on a mean, a really straightforward example. And then in histograms, I show, well, what is the actual data? And this is a sample size of 20. I've shown the data points. We've got frequency scale here. I'm using narrow bars than we might often do to give a more sense of showing the actual data points themselves. And then we could say, well, what do we think the population mean could be that these were selected at random from? Maybe 5 of them are below the population mean and 15 are above, just by random chance. Perhaps that could happen. Or 5 might be above the population mean and 15 below, just by random chance. And if you think that's more or less right for what you might get with random chance, then that pretty much agrees with this confidence interval. So this is a 95% confidence interval, shows quite a wide level of different population means are compatible with the data. But with a sample size of 20, the spread of what's possible for the confidence interval is a lot less than the spread of the data. This is a sample size of 500. And my experience is with these kind of explanations that students do quite readily get the sense that with a much bigger sample size, when they're selected at random from the population, you've got a much more precise estimate of the population mean and therefore a much narrower confidence interval. And explaining confidence intervals in this way, it does seem to develop this conceptual understanding and the sense of why confidence intervals are narrower with bigger sample sizes. And if students are actually interacting with these, there's some interactive exercises for them to figure out what the confidence intervals might be. This is the whole concept that it's about precision of estimate that will reinforce that based on assumed random choices and who you happen to recruit. Okay. Now we're going to talk about some research which McShane and Gall have done, which I find rather enlightening, somewhat concerning. They basically did surveys where they directly say this is the mean in one participant group, this is the mean in another, which is higher? Do we know? And if they had a small p-value, people say, oh yes, of course we know which is higher. If they have a big p-value greater than 0.05, people say, no, we don't know which is higher. Even when the question really strongly emphasises that the focus is on the participant means themselves, rather than generalising beyond that to the inference population. 85% of authors of the New England Journal of Medicine made this error in their survey, and around about half of statisticians. So the issue to me is when we're teaching, we put so much focus on, what happens when the p-value, if it's p is greater than 0.05, you don't really know which mean is higher. But often we forget to say that is true when you're making inferences to the population, assuming random sampling from that population. In confidence intervals, people much more often remind people that they're about the population, whereas with p-values, the culture is not to do that so much. And so if we are then interpreting a p-value as there isn't a difference, or we don't know that there's a difference, often in teaching we're not actually pointing out this is only applies to the population, assuming random sampling for that population. And so that's one reason why people would make this error. Again, what I'm recommending is different interpretations of p-values, and the following is one possible example. Study data shows low compatibility with being selected at random from a population where smokers and non-smokers had the same odds of death. So showed low compatibility, p is 0.006, with being selected at random from a population where both groups have the same odds of death. Within this is the assumption of random sampling from some population, and the focus on the population is clear, and it's a fairly short, simple sentence. And it's easy. And maybe this is useful for people to know, in addition to knowing the definition of what a p-value actually is. You can add extra to it. You can say the p-value is calculated over the assumptions of the statistical model to remind people of the importance of checking these assumptions. I'm not sure if it's worth putting this into the definition, but you could say, instead of selected random, by probability random sampling. Random these days can mean haphazard, bizarre, whereas probability random sampling, when you get big enough sample sizes, we have a certain amount of consistency between what we might get in estimates of a population mean. So there's minor tweaks, but essentially, again, you can use interpretations of p-values that might be better at really saying what they're about than some of the commonly used ones. Again, there's concern with excessive focus on whether p is less than 0.05. And so I've got this figure which illustrates the continuous nature of p-values. On the x-axis, we've got the z-value, which is a ratio of strength of association found in study participants to its precision. For instance, ratio of difference in means to the precision of estimate of the difference in means. And what do you mean by precision? Well, this is when we're using the study participant strength of association of an estimate of this association in the population from which study participants were selected at random. Okay, so when the ratio of the strength of association to its precision of estimate is about 2, or just over 2, we have this z value here. We can look it up here, and the corresponding p-value is going to be around about 0.03, which is somewhat low compatibility with random selection from population without such an association. If we've got a z value of 1 or even less, this is highly compatible with random selection from population without such an association. So there could easily not be any such association. We haven't got any evidence that there is that association in the population. If the strength of association is much bigger than its precision of estimate, say 4 times as big, we've got a very small p-value and very low compatibility with selection at random population without such an association. So that's my way of illustrating the continuous nature of p-values. To make this work, we've got the p-value on the log scale, minus log scale. It obviously isn't meant for people to find exact p-values, but it's intended to find approximate ones and to give a sense of how these things are linked. Now I'm going to summarise the ASA p-value statement, Guide to Good Practice. They recommend focus on estimation, odds ratios and confidence intervals are similar, which is one of the things I've been reinforcing in my suggested teaching strategies. Interpret the actual p-values, not just whether it's less than 0.05 or any other threshold. And they do recommend interpreting p-values in terms of compatibility with the data in the statistical model under the null hypothesis. And report their dependence on assumptions underpinning calculation methods. One of the key assumptions that people don't often seem to quote at all is the assumption of random sampling from some greater population. And that is an assumption that I feel it's really valuable for people to have reported on a regular basis, because otherwise how can people really understand what p-values and confidence intervals represent? That's how I see it anyway. They also recommend focus on scientific inference, study design, potential bias data collection methods, other supporting evidence, consistency with other studies. So rather than focusing so much on p-values, to focus more on these broader considerations. One of the challenging things, which I don't feel I've fully addressed, is the required pre-specification analysis plan for p-values to be fully valid. Otherwise, you're going to have issues of selective reporting. It is possible to add a sentence on the end of the p-value interpretation that reflects this. I haven't done it in practice when I've been teaching. I mean, there's challenging trade-offs between what level of understanding you can realistically expect. If you try and teach all the complexities all at once, then in my view, people might not really understand much at all. And so I guess this is a really important issue, but it's a bit more challenging to address. I have been teaching on a course where we've been talking about how you select predictors, what confounders do you adjust for. And as many people, we emphasise that you should choose them based on the literature rather than based on statistical choices, and so warning against stepwise procedures to choose the predictor variables, for instance. But that's not something I've addressed at all well in this publication. But other things I feel I have addressed quite well. And so this is my recipe book for promoting conceptual understanding of p-values and confidence intervals. And one starting point is educators should pay attention to known common errors of statistical interpretation in the research literature. And teaching methods should respond to these. So my recommendation in medical research is to refer to results and study participants, because that's really clear, makes it really straightforward what they are. Or you could use other language in different situations when they're not participants. And the next one, really say what confidence intervals are. So we could, for instance, say they're about precision of population estimate when generalising beyond study participants to some greater population, accounting only for random sampling variation, or accounting only for assumed random choices in their selection. Basically, some sentence that tells people the overall purpose of confidence intervals that I feel can be really quite lacking in some statistics courses. Interpret p-values continuously as level of compatibility with random selection of population with no such association. And the plot of p-values against z values is designed to encourage people to interpret them continuously. Okay, so that's my conclusion, that's my teaching recommendations. I'm Hilary Watt from Imperial College. If you're interested in these ideas, you can get in touch if you'd like. It's my publication. I'm doing ongoing work with Renata Medeiros Mirra, and she's from Cardiff University and from other co-authors as well, with surveys of people who've signed up for Burwalls Medical Statistics Teaching Conference and looking at how they interpret p-values and confidence intervals in practice. And there's some really interesting issues and stories coming out of that, and some actually really handy ways of interpreting confidence intervals that could be really useful for other people as well. And there's a paper under review linking the styles of p-value interpretations to a common major error with p-values. Another slightly separate thing is I've got excellent feedback on an R data wrangling management recipe book, which is basically how to get your data in order based on the assumption that people don't necessarily really know much R in the first place. And so it's written around practical tasks, which can make the job an awful lot easier. If you want a comedy video that I've done on science comedy, you can look at Google, YouTube, Hilary Watt, Florence Nightingale would get you the video. And I have got some teaching videos on my YouTube channel, although relatively few at the moment, and I'm intending to add more. So thank you very much, and thank you very much to the RSS Statistics Education Group. If you haven't already registered your interest, then I'm sure there'd be really welcome interest. And thank you very much for listening. Goodbye.